Welcome back to College Algebra. In this video, we're going to be looking at a couple of different things we can do with polynomial and rational functions, starting off with polynomial and rational inequalities. We've talked briefly about nonlinear inequalities in the past, so let's jump in with something like the quadratic inequality, x squared minus x minus 6 is less than or equal to 0. If we think about this inequality, what I want you to notice right away is that the corresponding equation, where we replace the inequality symbol with an equal sign, is something that we are already familiar with and we already know how to work with. So, in working with this equation, we might look at the factors. In this case, I would need two numbers that multiply to -6 and add to -1, like -3 and +2. Using the zero product rule, I get that this function has zeros at x equals +3 and x equals -2. I can graph that corresponding equation. If I wanted to be precise, I would go back. I would look for the vertex, figure out where that is. I'd plot the y-intercept as well to give me a little bit more data to work with. But plotting the two intercepts and recognizing that because the lead coefficient is positive, +1 in this case, the parabola will open upward. I know that the graph is going to look something vaguely like that. And that's good enough for our purposes for this problem. Because again, our goal is not to look at this equation. Our goal is to look at an inequality. What I want you to notice about this graph, something that would be true in general. In order for a curve to go from being positive, y is above the x-axis, to negative, y is below the x-axis, it has to go through 0. And the same thing happens over here. To go from the function being negative, or the graph below the y-axis, to being positive, it has to go through 0. And the inequality we have set up here is asking exactly that question. Where is this function negative? Well, it's negative in all of the space down here where it's below the x-axis. Where it's above the x-axis, it's positive and does not satisfy the inequality. We're looking at less than or equal. So I will include the points where the function is equal to 0, and we can write the solution set as the set from -2 to 3, right? Interval notation, closed brackets mean include that endpoint. Given a quadratic inequality, where we can graph the inequality, we can figure this out pretty readily. And the same argument is going to be true for any polynomial inequality. The only way that a polynomial can go from being positive to negative or from negative to positive is to pass through a point where the value of the polynomial is 0. So if we want to solve a more general polynomial inequality, say something like x plus 1 times x minus 2 times 3x plus 5 is greater than or equal to 0, we can look at the corresponding equality, x plus 1 times x minus 2 times 3x plus 5 equals 0, right? Again, this is called the corresponding equation. Conveniently for us, this is given in factored form, so we're able to solve it fairly readily. Using the zero product rule, one of these three factors must be 0. X plus 1 equals 0, or x minus 2 equals 0, or 3x plus 5 equals 0. Giving me solutions of -1, +2, and -5/3. We could continue on from here and graph this polynomial. That absolutely would work. But we don't really need that much detail. So we're going to think about what the graph would look like, but try to avoid the entire process of drawing out the graph because that takes a lot of work. The only thing that really matters for solving an inequality, as we saw in the last problem, is what's happening at the x-axis. So instead of drawing the graph, I am just going to draw the x-axis, a number line. And I'm going to plot these 3 points on that number line. Right? My scale might not be exact, but that's okay. It gets the point across. It'll be enough for what we need to do. I'm going to need a little bit more space over here, so let me extend this line out a bit. That's better. And again, remember, our question is just, where is the graph above the x-axis and where is the graph below the x-axis? And we know that the only places that it crosses the x-axis are these 3 roots. So if I pick any value over here to the left of -5/3, for example, -2, and I plug -2 into my equation or my inequality. Let's go all the way back to the inequality. So we will have -2 plus 1 times -2 minus 2 times 3 times -2 plus 5. Right? -2 minus 1 is -1. -2 minus 2 is -4. 3 times, sorry. 3 times -2 is -6. -6 plus 5 is -1. -1 times -4 is +4 times -1 is -4 again. And we're looking for places where we come out greater than or equal to 0. testing that, I like to put question marks above the equation or inequality. Is this actually greater than or equal to 0? And in this case, no. So we throw out that region. Nothing to the left of -5/3 will satisfy the inequality. Then we go to the next region. There's not a lot of space between -1 and -5/3. I guess -4/3 is there. That's something we can work with at least. And we repeat the process. Evaluate the inequality when x is -4/3. Right, so we get -4/3 plus 1, which is -1/3. We get -4/3 minus 2, which is -10/3. We get 3 times -4/3, which is -4, plus 5, which is 1. Right, -1/3 times -10/3 times 1 is positive 10/9. That's true. So this region does satisfy the inequality. I'll shade it in. I'm running out of space on the screen here, so I'm going to leave you to try a couple of other points. We need something between -1 and +2. A really nice, easy rule of thumb. Whenever 0 is in the interval you are testing, use it. It's always the easy one. But you plug in 0, you find out that that does not satisfy the inequality, so nothing in that region will satisfy the inequality. And then you try something over here to the right. To the right of 2, maybe 3 will work nicely. Plug in 3 in that inequality, and you will find that it does work. So we shade in that part of the number line. Last thing, if I scroll up a little bit to get to the original inequality, in this particular inequality, we are looking for greater than or equal to 0. And the 3 points that we originally plotted, -5/3, -1, and +2, are points where that expression is equal to 0. So those 3 points will also satisfy the greater than or equal to 0. We can go ahead and mark in that we want to include those 3 points in our number line. If we had an inequality that was strictly greater than 0 or was strictly less than 0, we would not want to include those 3 points. We'll see that in the next example. But to wrap this one up, we've now shaded in all of the places on the number line that satisfy the inequality. So the last thing we have to do is write the solution. And my preference is writing a solution in interval notation. It seems to be the easiest way to go about it. Remember again that square brackets mean include that point. We shaded from -5/3 to -1. Then we had a gap. Set union represents a gap on the number line. We started shading at 2, and we continued on indefinitely, which means we shaded all the way to infinity. Since infinity is not a real number you can ever reach, we don't include infinity in the interval. We use the parenthesis or open bracket to represent that infinity is not something in this interval. All right. I should have not scrolled down just yet, sorry. Looking back at the graph that we drew, there's a pattern of yes, no, or in this case, no, yes, no, yes. And you start to feel like there's just going to always be an alternating pattern, which is a dangerous trap to get into. Remember, based on the multiplicity of a zero, the graph of a polynomial may cross the x-axis at one of its roots, or it may bounce off of the x-axis and continue back in the same side. So if you have zeros of different multiplicities, sometimes you get some very strange patterns. For example, let's take a look at the inequality x times x minus 3 times x plus 2, the whole thing squared, is strictly less than 0. Once again, our method of solving a polynomial inequality, or really any nonlinear inequality, is going to start with looking at the corresponding equation. Just replace the inequality symbol with an equal sign. X times x minus 3 times x plus 2, the whole thing squared, equals 0. And since this polynomial is given to us in factored form, it's pretty straightforward to use the zero product rule. And find that we are looking at the solutions x equals 0, x equals 3, and x equals negative 2. So we draw out a number line. We plot negative 2, 0, and 3. As I said in the last example, it doesn't matter if you are very precise with your distances, although it does matter that you actually get things in the number order that a number line expects. Otherwise, very strange things would happen. And then once we have this number line, we pick a couple of points in between. So we look for something to the left of negative 2. Negative 3 might be a nice choice there. We look for something between negative 2 and 0. Negative 1 seems to fit that bill. We look for something between 0 and 3, like positive 1. And we look for something to the right of 3, like positive 4. We evaluate the original inequality at each of these points. So for the first point, we take x is negative 3 times negative 3 minus 3 times negative 3 plus 2, the whole thing squared. That's going to be negative 3 times negative 6 times negative 1 squared. Negative 3 times negative 6 is positive 18. Negative 1 squared is 1, and multiplying by 1 does not change anything. We are asking if this is strictly less than 0, and it is not. So I will mark that that came out false. Then we have to continue evaluating each of the other 3 points and determining whether the inequality is true or false at that point. Pause the video and take a moment to write that out on your own. For the sake of screen space, I'm not going to go through those calculations. I'm just going to give you my results. All right, so when we plug in x equals negative 1, I end up with positive 4, which is not less than 0. So that's false. When I plug in x equals positive 1, I end up with negative 18, which definitely is less than 0. We get true in that region. And when I plug in x equals 4, I get a relatively large number, 144, which is definitely not less than 0, so we are false in that region as well. The only space where this comes out as true is this part here between 0 and 3. Since we're looking at strictly less than 0, the places where the polynomial is equal to 0 are not solutions to the inequality. So I'll put an open circle at 0 and at 3 to remind myself that I do not want to include those when I write the solution set in interval notation. Points that you do not want to include, you use a parenthesis, an open bracket. So not including 0, but everything after 0 to 3, and not including 3 is the solution set to this polynomial inequality given in interval notation. If we consider a rational inequality, there is one other thing that we have to worry about. For example, if I want to solve the inequality 1 over x minus 2 is greater than or equal to 0. The rational function 1 over x minus 2 does not have any zeros, but it does have a vertical asymptote when x is equal to 2. So if I want to graph y equals 1 over x minus 2, I notice that there's a vertical asymptote when x minus 2 is equal to 0, which means that x is equal to 2. I draw in that vertical asymptote. I can evaluate this when x is 0. That's negative 1/2. So 0, negative 1/2 is a point. And I can sketch out the graph y equals negative 1/2 to see it looks something like this. And the big takeaway I want you to get here is that the graph of this function changes from negative to positive in this case at a vertical asymptote. And you can also change from positive to negative at a vertical asymptote. So to solve the inequality, we look for the places where the curve, in this case, we are looking for greater than or equal to 0. And that's the stretch over here. Does not include 2 itself because the function is undefined when x is equal to 2, but everything to the right of 2. So open interval from 2 to infinity is the solution set to this inequality. So when you are dealing with a rational inequality, Very similar to a polynomial inequality, you're looking for zeros, places where the graph crosses the x-axis, but you also have to look for discontinuities, places where the graph has a vertical asymptote and it might wrap around. Just like when we were dealing with polynomial inequalities, we can look at how these rational inequalities behave around the x-axis, and that's enough for us to be able to work with the inequality. So for example, let's consider the rational inequality x plus 3 over x squared minus 2x is less than or equal to 0. Just like when we solved the polynomial inequalities, just like we saw in that last example, in order to solve a rational inequality, the first thing I'm going to do is look for the corresponding equation, x plus 3 over x squared minus 2x is equal to 0. And if the denominator, x squared minus 2x, is not 0, we can multiply both sides of the equation by that denominator, leaving us with x plus 3 is equal to 0. Right? The unequality, x squared minus 2x not equal to 0, we can solve by factoring. There's a common factor of x, leaving behind x minus 2. And the zero product rule works for an unequality just the same way it does for an equality. We see that x is not 0 and x is not 2. So as long as x is not 0 and x is not 2, the solution to this equation is x equals negative 3. Right? If x is 0 or if x is 2, that means that the denominator of the function is undefined and we are likely to have a vertical asymptote. So when we are looking at places where weird things can happen, we are looking at places where the function can be 0. We are looking at places where the function is undefined. And that gives us some regions that the number line is divided into. And we test in between those regions the same way we did for the polynomial inequalities. Right? Again, by focusing just on the x-axis, it saves us the effort of having to deal with trying to actually graph the rational function. And since the problem is not asking us to graph a rational function, that's effort well saved. So let's take something to the left of negative 3, like negative 4. Let's take something between negative 3 and 0, like negative 1. Let's take something between 0 and 2, like positive 1, and something to the right of 2, like 3. Test the original inequality at each of those points. So plugging in x equals negative 4, we have negative 4 plus 3, which is negative 1, over negative 4 squared, which is 16, minus 2 times negative 4, which is plus 8, negative 1 over 24. And we're looking for less than or equal to 0. And negative 1 over 24 is in fact less than or equal to 0. And because we are true there, we are true everywhere in that region. Everything to the left of -3 does satisfy this inequality. Then we evaluate at x equals -1. Once again, I'm running out of screen space, so I'm not going to go through each of those calculations. If you'd like to pause the video and work through those yourself, I encourage you to do so. When I plug in x equals -1, I get positive 4/3, which is not less than or equal to 0. So we are false in that region. When I plug in x equals +1, I get I get -4, which is definitely less than or equal to 0. So we're true in this region. When I plug in x equals 3, I get 3, which is positive, not less than or equal to 0. So we're false there. All right. So I fill in that region between 0 and 2. The other two regions stay empty. Great. For a rational inequality, the boundary points are a little bit more confusing. We're looking for less than or equal to 0. And equal to 0, we saw -3 works. So -3 is a point in this interval. If we were looking for strictly less than 0, then -3 would not have been a point. 0 and 2, though. 0 and 2 are places where the function is undefined. So if you plug in x equals 0 or you plug in x equals 2, you do not get a solution to the inequality. We need to throw those 2 points out. So going to the left forever, that means we start at -infinity. We can never be equal to -infinity, so I use the parenthesis, the open bracket, to say not including -infinity. That continues all the way to -3, which we said was included. So nice square bracket there to include that. Then there is a gap. Set union is the way to represent a gap in interval notation. And then starting at 0, but not including 0, and going to 2, but not including 2. There is the interval notation for the solution set to this inequality. Let's take a look at one more. Let's take a look at a couple of examples that exhibit some strange behavior that rational inequalities can have that polynomial inequalities very rarely do. First of all, how about x squared over x squared minus 4 is greater than or equal to 0? And we will analyze this as though it was the equality x squared over x squared minus 4 equals 0. Because we are looking at the inequality greater than or equal to, right, the equals 0 is solutions. And as we saw in the last problem, the points of interest are going to be either that the numerator is equal to 0, which will satisfy the greater than or equal to inequality. If we had a strictly greater than inequality, this would not. And then the denominator, x squared minus 4, not equal to 0. Right? When the denominator is 0, the function is undefined. So those are never going to be solutions to the inequality, no matter what the inequality symbol looked like. Right. So if x squared is equal to 0, that means that x itself is 0. If x squared minus 4 is not equal to 0, there's a couple of ways to think about this. I recognize this immediately as the difference of squares. X plus 2 times x minus 2 is not equal to 0, which means that x plus 2 is not equal to 0, and x minus 2 is not equal to 0, which means that x is not negative 2, and x is not positive 2. So we have 3 points of interest to sketch onto a number line. Negative 2, 0, and positive 2. And then, as we have been doing, pick a couple of points representative of each of the 4 regions this divides the number line into, like negative 3, negative 1, positive 1, and positive 3. And once again, I don't have the screen space to evaluate all 4 of those points, but go ahead, pause the video, plug x equals negative 3, x equals negative 1, x equals positive 1, and x equals positive 3 into the original inequality and see where the inequality is true and where the inequality is false. I get that when you plug in x equals negative 3, this comes out true. When you plug in x equals negative 1, this comes out false. When you plug in x equals positive 1, this comes out false. When you plug in x equals positive 3, this comes out true again. So, shading regions. We want to include all of this stuff to the left of negative 2. We want to include all of this stuff to the right of 3. And we want to think about our endpoints, because x equals negative 2 and x equals positive 2 are not solutions to the inequality. They're places where the left-hand side is undefined. So those are things that we want to put an open circle on and not include. But x equals 0 is a solution to the inequality. That's a place where this function is equal to 0. The left-hand side is equal to 0. And because we are looking at less than or equal to, that still satisfies the inequality, and we need to include that point. There are a couple of ways you can do that in interval notation. I think the easiest is to just put a singleton set in the middle. So we have everything to the left of negative 2, not including negative 2. We have a gap. We have the point 0. We have another gap, and we have everything to the right of 2, not including 2. It gives us a kind of interesting looking interval, but it works, so we'll go with it. One last example that kind of exhibits the opposite of this behavior. Let's take a look at, x minus 5 over x squared is less than or equal to 0. Once again, I'm looking at less than or equal to, which means places where this function is equal to 0, specifically where the numerator is equal to 0, will be solutions. So we set the numerator equal to 0, and we remind ourselves that the denominator is not 0. And we have 0 and 5 as our two key points. A little bit simpler than the ones we've been doing. There's fewer points on the number line, which means fewer regions. But we go ahead and graph the number line. We find a couple of key points. We evaluate the function at each of those points. When x is -1, we have -1 minus 5, which is -6, over -1 squared, which is +1. -6 divided by 1 is -6, which is in fact less than or equal to 0. So we're true here. Put in x equals +1. We get -4, which works. Put in x equals 6, and we get 1/36, which is positive, does not work. So, shading in, we are interested in this part of the number line. We are interested in this part of the number line, and we're not interested in the part to the right. From what we said before, x equals 5 is a solution, so we'll fill that in with a closed circle. But x equals 0 is a place where the function is undefined. So we'll put an open circle there to remind ourselves we don't want to include that point. And once again, this gives us a relatively goofy thing going on in the interval. We have everything to the right of 5 except for 0. And there are a couple of ways you can write that out. I think that the most straightforward is to think about this in two groups. We have everything to the right of 0. We have a gap. It's a very tiny gap, but it is still a gap. And then we have everything from 0 to 5. So we can write out the solution set for this inequality in interval notation as well. Changing gears, I next want to talk about the problem-solving idea called variation. Variation is a generalization of proportions. You're familiar with solving problems like an architect's scale has 1 inch on the paper representing 5 feet in a building. And asking questions like, how long is the representation of a 17-foot wall? We set that up as a proportion. The scale, 1 inch over 5 feet, is equal to the scale that we don't know, x, over the distance in the world, 17 feet. We can solve this problem using the cross product test. 1 times 17 is 17. 5 times x is 5x. Getting x by itself, that's 17 over 5. And because this is an application problem, it probably makes more sense to give that as a decimal number. 3.4 inches is the value of x. That kind of reasoning should be old hat to you. In variation, we're going to do two things. First of all, we're going to look for a repeatable rule so that if you are trying to find the scaling for many walls, right? You are creating the architectural plan and you have to draw in wall after wall after wall. Can you do it faster than setting up a proportion and solving the proportion every time? The answer is, of course you can. The other more fascinating thing we are going to do is sometimes this kind of problem is called a direct linear proportion. And our goal is going to be to look at a nonlinear proportion in order to be able to solve the same thing. And that's where I want to focus our work today. The phrase y is proportional to x means about the same as the phrase y varies with x. Or to be explicit, we'll often say y varies directly with x. Whenever you see phrasing like this, you should interpret that as telling you that we want an equation that looks like y equals k times x for some constant k. If you know a particular situation, then you can use that particular situation to figure out the value of k. And then if you have the value of k, you can use that to figure out more situations, right? If you know what k is and k is constant, then if you pick a different x and y for the same situation, if you know one, you can calculate the other. The place this becomes interesting is not with direct variation, although it does certainly work. It's when we start introducing more to the variation. Instead of y varying with x, we might have that y varies directly with the square of x. So if y varies with the square of x, in my variational equation, instead of writing x, I will write the square of x. Y equals k times x squared. Then if we know some particular values for a particular situation, say y is 4 when x is 5, we can plug those things into x and y and write out the equation. 4 equals k times 5 squared. 5 squared is 25. And to get k by itself, we divide both sides of the equation by 25 and get that 4 over 25 is the value of k. Now, again, the key for these ideas of variation is that k is a constant with respect to x and y. For the particular situation that we are talking about where y varies directly with the square of x, we have found that k is always 4/25. So we can plug that back into the original equation and write that y is equal to 4/25 times x squared. And that's useful because we might be looking at another situation that we are interested in. What is the value of y when x is 7? Well, since we have an equation that only has x and y in it now, we can put this into that equation. I don't know what y is. I know that k is 4/25, and I know that in this case, x is 7. 7 squared is 49. And 49 times 4 is, let's see, 4 times 4 is 16. 9 times 4 is 36. 160 plus 96. 160 plus 36 is 196. So y is 196/25. And so we found the value of y when x is 7 for this particular situation. Putting the variation problem into context, the distance a person can see to the horizon varies directly as the root of the height that person is above the ground. At a height of 50 feet, the horizon appears 14 miles away. How far away will the horizon appear from a height of 120 feet? I could choose to use y and x and set this up as a very generic looking variation problem. But I generally find that I am more successful if I use variables that seem to make sense for the problem, because that way I can remember what they mean. So we are looking at the distance a person can see to the horizon. That's a distance, let's call it d. And d varies directly as the root of the height that person is above the ground. Right? It is a height, we will call it h, and we want the root of that height, so not just h, but square root of h. So what we're really looking at is d varies as square root of h at a height of 50 feet, that's h equals 50. The horizon appears 14 miles away. The distance to the horizon, d, is 14. How far away will the horizon appear? What is d when you are at a height of 120? So h is 120. We can take this paragraph and rephrase it in a very abstract sense, which gives us exactly the tools we need in order to set it up as a variation problem and solve from there. Having done that, I don't need the paragraph anymore. I just need the statement I wrote out. So if d varies as the square root of h, that means that d is equal to some constant k times the square root of h. If h is 50, d is 14. 14 equals that same constant k times the square root of 50, which means that 14 over the square root of, that's not a 5 at all. 14 over the square root of 50 is the value of k. And my calculator is happy to give me an approximation. 14 divided by the square root of 50 is something in the ballpark of 1.98. Then I'm asked, what is d when h is 120? So d equals k, which is 1.98 times the square root of h. And in this particular circumstance, h is 120. And my calculator is happy to tell me that 1.98 times the square root of 120 is something in the ballpark of 21.7. And that was measured in miles. On a problem in the homework or on an exam, pay attention to instructions. A problem like this, I would probably give you instructions of round your solution to the nearest tenth of a mile to indicate to you that I want you to grab a calculator, punch things into a calculator, and get an exact number out, or get a decimal approximation out, not an exact number. Looking at this from another direction, variation, direct variation, tends to mean multiplication. Multiplication is often useful, but so is division. So if we want not to have multiplication, the inverse of multiplication is division, and phrases like y varies inversely with x or y is inversely proportional to x tell us to set up a variational equation, y equals k divided by x. Other than that change, the rest of the process looks exactly the same. And in fact, just like we did with the direct variation, very often we're not going to be looking at inverse variation in a linear sense. Although let's go ahead and take a look at that first. Y varies inversely with x, and y is 12 when x is 8. Right? Because we're dealing with inverse variation, that means we're looking at the equation y equals k over x. We have a couple of numbers in question. 12 equals k over 8. Multiplying both sides of the equation by 8, we get that 96 is the value of k. And again, remember, the key of variation is that for a particular situation, k is constant. So if x and y vary, k stays constant, which means that instead of the generic y equals k times x, we now have the specific equation for this scenario, y equals 96 over x. And then if we have something to work with, we can solve from there. What is the value of y when x is 24? Well, just plugging in, y is 96 divided by 24, and 96 divided by 24 is 4. So same principle as a direct variation will allow us to solve an inverse variation problem as well. The intensity of a light source is inversely proportional to the square of the distance to that source. If a car's headlights have an apparent intensity of 0.8 foot candles from a distance of 100 feet, how intense will the headlights appear from a distance of 5 feet? Once again, we are looking at a situation where we are trying to apply the ideas of variation. And as with the last one, we could choose to simply use the generic variables of x and y if we would like. But I find that it's easier to figure out what's going on if I use letters that remind me of what these things mean in the situation. So we're looking at the intensity of a light source. Let's call an intensity I. It's going to be inversely proportional to the square of the distance to that source. Wrong color pen. There's the red pen, the square of the distance to that source. Right? It is a distance, so let's call it d. And we'll notice that we are squaring d. So not just d, but d to the second power. Right? So I is inversely proportional to d squared. If a car's headlights have an apparent intensity of 0.8 foot candles, that's I equals 0.8, from a distance of 100 feet, when d equals 100. How intense will the headlights appear? I is unknown from a distance of 5 feet, when d is equal to 5. Taking paragraph of information and abstracting away and saying, we don't care about the fact that we're talking about a car's headlights. We don't care that we're talking about the intensity of a light source. We're just talking about some measured thing called I. We don't care that we're talking about the distance that we are away from the light source. We're just talking about some measurement we call d. So I is inversely proportional to d squared. And having written down those couple of pieces of information, we don't need the paragraph of text anymore, although I do need the first line of that information. So forgive the wiggling as I scroll back up just a little bit. All right. I is inversely proportional to d squared. I equals some constant over d squared. I equals 0.8 when d is 100. So 0.8 is equal to some constant k over 100 squared. 100 squared is 10,000, and multiplying both sides of the equation by 10,000 gives me that 8,000 is the value of k. And again, but remember the whole idea of variation. I and d are variables. They are going to vary, hence the name variation. K is constant. For this particular car's headlights, K is always 8,000. So I can substitute that in my general rule, instead of I equals K times D squared, is I equals 8,000 over D squared. And then the problem asks me specifically about the situation when D is 5. Right? 5 squared is 25. 8,000 divided by 25 is 320. And our intensities, if we scroll back up to the wall of text, our intensities were in foot candles. So from a distance of 5 feet away, the apparent intensity will be 320 foot candles. What a foot candle means is completely irrelevant to the problem at hand, although I can tell you that a foot candle is the light that you experience by burning a candle 1 foot away from your eyeball. So the apparent intensity of staring at these headlights from 5 feet away is the same intensity as burning 320 candles 1 foot away from your eyeball. Don't stare at cars' headlights from 5 feet away. It's a bad idea. With that, we will wrap up this idea of variation and the lesson here. Thank you for joining me. See what you can do with these problems now, and I'll see you in the next video.